Hi, it's Wednesday, March 25th, and we are currently starting a new topic, kinetics and equilibrium. Uh, I have yet this morning to look at the grades and get them on Power School. I'll be doing that, and I know some of you had difficulties with the programs. We're going to work out a protocol for that, so just be patient. Let's get today's lesson and new topic started. Last topic was, I don't want to say easier, but it's a little easier than kinetics and equilibrium. Plus, we had most of the learning done face to face. We're starting from scratch remotely, so let's see how it goes. Also, those of you that might not have your book at home, I'm working on the assumption that all of you have it. If you don't, reach out to me. I'll see if I can figure something out. Leave one up at school. Get it to you somehow. I'll figure that out. Or if I have to like photocopy pages or post pages somehow. But if you all have it, I don't have to worry about that. So if you don't have it, tell me. I'm gonna proceed today with the assumption that some people might not have their book. But if I hear everyone has their book, it'll be a little easier for me because we'll just do the underlining like we did in class. Here I'm going to be doing some of the writing just in case people are going to be taking notes to move forward with the topic. If you do have your book in front of you, though, turn to page 135. And on page 135, you're going to see a picture of a couple of cars crashing. Our topic is kinetics and equilibrium. They're two separate things, kinetics and equilibrium, but they are in fact intertwined. Kinetics deals with collisions of molecules and reaction rates. Equilibrium deals with forward and reverse reactions and the movement of reactions back and forth. We've talked about equilibrium in saturated solutions and in phase changes. Now we're going to talk about it in regards to chemical reactions. Kinetics portion first. I'm only really going to deal with kinetics today and then hopefully review it a little bit and then get into the equilibrium portion and then see how we go from there with review. Right? If you're looking at page 135, you see a picture of a couple of cars, okay? And the cars are in an accident. They're having a collision. In order for a chemical reaction to happen, the particles have to collide. Two particles collide. Now, they can collide kind of like this, missing each other, or collide square on. In order for a reaction to happen, there are two ingredients for that reaction to happen. One, the way it collides, and then two, the energy of collision. I like the example of a car accident. I teach driver's ed, so I can relate to that. But I think a better example is hitting a ball, say with a bat, right? I'm sure each of you here has at least watched a baseball or a softball game at some point in time, or even golf, right? It's the same principle. You have to have two ingredients to get that 400-yard drive or to hit the baseball over the fence, right? You have to hit that ball hard enough and with the proper trajectory, proper orientation to get it up and over the fence. You can hit the ball with all your might, Mark McGuire, or I don't know who you want to use as an example, Pete Alonso, right? They can hit the ball with as much force as they can possibly muster, but if they don't get on the bottom half of that ball to give it lift, it might just be a line drive down onto the ground. In order for it to go over the fence, you can hit it with the upswing, the trajectory, but if you don't hit it hard enough, an outfielder will catch it. So the two ingredients are force of impact, orientation, and if we can turn the page, okay, these ingredients make what we refer to as, I'm going to write some of this stuff down. Look, I went out and got myself new markers yesterday because if you're remembering the other day, I was having trouble with some of the writing. Whoops, sorry, Harry, your dog's under my feet. All right. So these are the ingredients that go to what we call an effective collision. And it is proper orientation and sufficient energy. Okay, I'm going to tell you where to note these things in your book if you have your book with you. But if you are on page now 136, to the left of where it says kinetics in that left margin, I would simply write the word effective collision. And then on the second to last line, you're going to see spatial orientation. Sometimes it's referred to as geometry. And then it says energy of colliding particles. Those are the two ingredients to an effective collision. Okay. And what did I see? Which phrase did I see? Effective collisions in here. I missed it. I'll probably come to it. I did underline it somewhere. But okay, we're going to continue. All right, now we're going to get into rate theory. Okay. Chemical kinetics is important because if you're in a manufacturing facility, maybe trying to make the new drug for coronavirus, you're going to need to produce that drug as quickly as possible. So an understanding of kinetics will get you to produce that faster, get it out to market faster. Bottom line is this, the faster you can do something, the more potential money you can make. So chemical kinetics is a huge multi-million-dollar industry. And right now, it's probably the most important thing out there in terms of trying to decide what new drugs could be used and how quickly it can be manufactured. All right, so the factors that affect rates of chemical reactions. The first one, okay, actually there's a general statement here, factors affecting rates of reactions. Starting the third line up, there are 6 factors that we're going to talk about. And then in that paragraph, it summarizes something that says, all these factors affect rates of reaction by changing the number of, and there's that word, effective collisions that take place between the particles. All right, and I'm going to talk about the factors. I'm going to write a brief summary on the board as I go along, okay? First one is nature, okay? And then in nature, what I'd like you to do, third line underneath, write slower. No, I guess we got to start in the line above. Second line down, middle sentence, it says, in general, covalently bonded substances are slower to react than ionic substances. So I'm going to write down a summary point for that. You can underline it. If you're not, you're taking notes, you're going to write covalent, slow, ionic, fast. Yeah, so again, we got to remember our points of bonding. Okay, when it's metal on metal, it's an ionic compound. And when you see a reaction between metals and nonmetals in a liquid solution, that's going to be the fastest because solids really don't react very well. Ionic substances, when either liquefied or dissolved in water, are the fastest reactions. And if you remember the precipitate reactions that I showed you, I poured, one liquid into another, and we got this white. It turned completely white, but then it settled. I showed that to you shortly before we went on our remote learning hiatus. I demonstrated that to you. I don't know if you remember it or not, but if we get back in the classroom, maybe I can show it to you again and have you perform it yourself. All right, so that's the first one, nature. Second one says concentration. All right, first sentence in there is the most important. It says most chemical reactions will proceed at a faster rate if concentration, and then blah, 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 is increased. That's what you underline. And again, it says most because there are exceptions to this. There are what they refer to as zero-order reactions, which goes more into like advanced placement and college-level chemistry. But those zero-order reactions are not concentration dependent. You can add as much as you want. It's not going to change anything. So the next one is going to be increase in concentration. It's going to make it faster. Next bullet. If you're working with the textbook, you're going to see the next one says surface area. I'm skipping that. I'm going to pressure. The reason why I'm going to pressure and concentration is really the same thing. We change the concentration of a gas by increasing the pressure of the gas, right? To increase pressure, you decrease volume. So you take it and put it smaller, okay? There's going to be less space, so the molecules are more concentrated. There's more of them in the same area. So an increase in pressure is going to cause more collisions. Okay, so increase pressure also is going to be faster. I can give you a couple of scenarios to help you understand this. Imagine taking one room in your house. Now, don't do this because we're supposed to be maintaining social distancing. But if we weren't maintaining the social distancing standards that we are now, you'd be able to do this, right? Pick a room in your house, take all the furniture out, ask people to walk around blindfolded, say 5 people, right? Then count the number of times they bump into one another. Give it a number. Doesn't matter what it is. Then put another 5 people in the room. Now you have 10 people in the room walking around. Are they going to collide more often? By having more particles around, a greater concentration of particles, you increase the likelihood of a collision. If you increase the likelihood of a collision, you increase the likelihood of an effective collision. Pressure, okay? Let's say we have 10 people in a room, okay? Say a rather large room, right? Maybe your dining room or living room or a larger room. Then take those same 10 people and put them into a small room or the smallest room in your house, which is probably the bathroom. Ask them to walk around. Now they're in smaller space, they're going to collide more often. Thus, increasing pressure by decreasing volume or adding more molecules is going to increase the concentration. Increase in concentration increases rate. I skipped over surface area. I wanted to put pressure and concentration together because it makes more sense to me. The textbook kind of separates them. I don't agree with it. It's really the same thing. Going back to surface area, think about this. If you wanted to sweeten a drink, if you would use a single cube of sugar or powdered sugar, what's going to mix into your drink faster, the powder or the single cube? What's going to make your drink colder faster, crushed ice or a single ice cube? When you have smaller particles, you have more surface area. That means there's more contact between the solution and the substance that you're adding. Okay, so increased surface area. That would be powder. All right, would be faster. Okay, and then catalysts. Okay, catalyst section. We're going to talk about it more when I go on to reaction diagrams in a couple of minutes. A catalyst is a substance that's added that changes the way it happens. I'm going to describe the catalyst more later on, but I'm just putting catalyst, makes it faster. It creates something called a new mechanism, but we don't know what the mechanism is yet because I haven't gone through reaction diagrams. So the concept of a mechanism is beyond us. And then the last one here is temperature. Temperature is the big one, and it's probably one of the easier things to do to increase the rate. Okay, so I'm putting the last bullet here, increase in temperature. Reactions are going to be faster. And think about it. At higher temperatures, how do particles move? Faster, you say. Very good. All right. So when particles are moving faster, they can collide more often. If they can collide more often, the probability of an effective collision increases. Not only that, there's a frequency factor. It's twofold. You have a greater number of collisions if they're moving faster. So with higher temperatures, you get harder and more frequent collisions. Okay? Let's try moving on to the next section. We're going to skip those questions. I'm going to go over the questions, I think, tomorrow with you. If you have your book, you can try them tonight, if on your own if you'd like, and then I'll discuss each one just like I did last time. I'll read through them just in case people don't have the books. But reach out to me if you don't. We'll see what we can do. All right. Potential energy diagrams. All right. We've actually seen the potential energy diagrams before when I talked about endo and exothermic reactions. So the shapes of them should not surprise you. right? But what they do is they show the general energy transitions as we move from products to reactants. Right. There are 4 levels in them, and these levels are going to allow us to determine whether a reaction is endo or exothermic. Maybe I'm going to contrast 2 of them very quickly, then show you how to label them. Okay. We have the exo and the endo. All right. In exothermic, energy is released. So we're going to start high. We always have to have this activation energy hill, and it goes lower at the end. And in endothermic reaction, we start low. We always have the activation energy hill, and it ends up being higher. So this represents the energy going in. This represents the energy going out. Okay. Now, when we write these things out, there's 4 levels of energy that we have to denote. All right. So I'm going to set this up as a grid. All right, on a graph. All right. This bottom line, this is the baseline. This is the point of 0 energy. Sometimes they use lightning bolts in these things. I have a tendency to try to always draw them with the 0 at the bottom. It makes for better understanding. And especially if you're labeling lines, which if you're looking right now on pages 138 and 139, or actually on 139, you see these diagrams with lines on them. You need the baseline to be at 0 for it to actually be accurate. But let's continue on, and I'll see if I can get you to understand it. You're going to have 4 levels after this. Okay, the highest level is going to be where the activated complex is. So I'm going to write activated complex. That's the top of the curve. Okay, if you're looking on page 139, the little diagram top left, you see that activated complex. It's an intermediate structure that's between reactants and products. Now, these 2 lines are either our product or reactant lines. The heights of them are going to differ whether it's exothermic or endothermic. In an exothermic one, the reactant is going to be higher, the product lower. In an endothermic, the reactant is going to be lower, the product higher. So for these 2 lines, it's always going to be reactant R first, P at the end. So I'm just going to draw one using all the levels. I'm going to start here, go up to the activated complex, down to the product. Excuse me. This is an endothermic reaction. Okay, reactants first, products last. All right, the activated complex in the middle. I can change this one. And now I'm going to draw the exothermic. Start high, go up. This one goes all the way down. And that's the exothermic. Reactants here, products here. So the height of the activated complex is always above products and reactants. We're always going to start at a baseline of 0. And then there are 6 lines that we're going to label on here. And that's probably going to be the lesson for today. All right. The 6 lines. There are 3 lines that are going to touch the bottom. The lines that touch the bottom are going to be potential energy lines, PE. Right? So you're going to have PE of this height, which is reactants. PE of the activated complex. PE of the products. And then we're going to have 3 lines that, 3 lines that touch the top. We're going to add 2 more lines because we already have one that touches the top. There's 1 line that's going to go from bottom to top. The other 2 lines are called activation energies, AE, I'll abbreviate it. From here to the top, this is forward. activation, energy. And this one from products to the top is reverse, activation, energy. All right, so we have 3 lines that touch the bottom, 3 lines that touch the top. There's going to be a line that's between products and reactants. And this line is called delta H. It's the change in heat. It represents the heat energy absorbed or released during a chemical reaction. Catalyzed line, I'm not going to look at that today. All right. What I think I'd like you to do, okay, if you have your book with you, you can do 1 through 10 on pages 137 and 138. If you don't have a book, let me know as soon as possible. I don't think anyone's reached out to me yet saying that they haven't. But I'll see what I can do, if I can take pictures of the pages and post them or whatever. I don't know of any other way to get them online. And on the reaction diagram ones, you know what? I think you can do through 17. Wait, no, you might not be able to do 13 because that asks for a specific amount of energy. I'll talk to you about the amounts of energy tomorrow. That's the last of the reading on 140. So since I'm not going through lessons with you on 140, skip that and skip question 13 and do through 17. Right? I'll see if I can get some other practice problems maybe uploaded so you can have a little additional practice. But we'll do these first, okay? If you have any questions, email me, post on the log. You can even message me through Edmodo. I've actually gotten some of those and gotten back to people. Anyone that's contacted me, I've gotten back to you. All right. Have a good today. Have a good day today. Stay safe. Stay dry too, because I think we'll have a little bit of rain. So it might be good to do as much studying as you can, because you can be indoors anyhow. Tomorrow might be nice though. All right. Take care. Bye.